Work? Yes, thank you very much. And well, it's a great opportunity to be here. So today this talk is closely related to the previous one, and Tamas has introduced in his usual careful and I would say very accurate language a lot of things that I would have described in a much rougher terms. So it's great. So I will talk today about multistability, and I also try to draw a line also to, in general, to the concept of response system, of a system to perturbation. So a lot of people have been interacting with me on this, and of course, first and foremost, Tamas himself, and also, unfortunately, a person that I would have loved to be here, but is not here because he's not with us anymore. Bruno Eckhardt, some of you might know him, is really one of the most inspiring scientists I've met in my life, and huge inspiration for this work, as well as for the work on unstable periodic orbits that I think Andrei partly will talk about later. And unfortunately, he passed away at a very early age. And well, I was very shocked because I had invited him, and he's a person I would write email and asking for a suggestion and ideas. So too bad, really. Let's, before we go on the gritty part, let's look at the glam part. So I had the huge privilege of having been invited last year to present the movie Melancholia by Lars von Trier at Barbican. It's a very, one of the coolest places in London you can invite to do things. And this was the London Mathematical Lab, a bizarre and fun institution based in London. In fact, I think Davide Farandi is affiliated to it. They organize a cycle of seminars associated to movies, and so they asked me to present a movie about critical transition, and I chose this movie because this movie indeed was the inspiration for a lot of the work in this area. As cliché as it sounds, this is how it happened. And something instead, I would say substantially less glamorous, Michael, if you allow. This is a preprint paper that Michael and I put on archive. It's been the effort of 3 years of work, which is nowadays unusual. We're used to writing short stuff and sort of a short cycle of learning, writing, publishing. So this is the opposite, and it's extremely inefficient, and I'm very proud of it because I learned a lot of things, surprisingly. And so that's, you're invited to give a look and send feedbacks. We're already receiving some, and thanks. So I am using some color coding to present today. So black is the introduction, blue is the deterministic dynamics, and orange is the stochastic part, which will be hopefully the most interesting today. So the general class of problem, as I was mentioning earlier, I'm interested in is, actually this is since really I started science in condensate matter, is about studying the response of systems to perturbations. And with what time has been growing, I was interested in electrons perturbed by light, and then things changed, and I realized there is a large class of problems that go under this huge label. In fact, it's a big label covering a lot of things we do in general in science. So the problem of sensitivity of system to perturbation, and the concept of climate sensitivity is one of the many manifestations of this. The concept of robustness of the system, which is essential in dynamical system, as well as when we construct numerical simulations of it. And then the sort of two extreme regime of response, the smooth response, which is what we like because we can predict how the system will change when we perturb it, and the opposite regime of critical transitions, where this is crazy things happen, and of course interesting things as well happens. Now, briefly, the smooth response, as I said, is a huge, of course, each time we linearize, we assume this works, okay? That's what, and, I didn't lose anything yet. So in statistical physics, the first systematic contribution of this came from Kubo, who produced a theory which works extremely well, despite being wrong, both in physical and mathematical terms, if you look at it with enough care. So it's an interesting case where it was extremely non-rigorous, but extremely correct and very, very useful. We can discuss, let's say the reason why physically it doesn't work is because of the lack of thermostats. that stabilize things. This was implicitly mentioned in the presentation yesterday. The problem that if you perturb a system that lives, obeys an Hamiltonian, you need to put a thermostat to take the energy out. Mathematically, there was no analysis, basically. And this has happened later through the work of first of Rouel in a deterministic system, and then Lucarini and Vivian Baladi. And this is actually next week. There will be a workshop from the 14th to the 16th dedicated to response theory, okay? And from a stochastic dynamical point of view by Heyer and Maida in 2010, and many, many other contributions. Those of you who are interested are strongly recommended to come to the seminar next week. And instead, if we go into the regime of critical transition, it's actually vastly different literature, and the previous speaker gave a very, very good introduction to the class of problem we want to mention. And let me add on the top, Tamas mentioned the Friedel-Wenzel theory, and allow me to skip a few slides. If you want to give a cultural embedding to this, in the 60s, I think probably in these rooms or nearby, Collège de France, École Normale, and so on, René Thom proposed on one side, Arnold from a different, of course, a different location, different point of view, the idea that qualitative properties of dynamical system is, there is a transitions between different classes of qualities, I would say, dynamical system through catastrophes. And this was a huge thing, which somehow subsided, but I think it's hugely relevant and with a different name. And something, a paper that I think has the great merit of providing a classification. When we study complex systems, we lack ability to see clearly things. So I think papers who provide clear classifications are extremely useful and pedagogical, as well as to teach us how to think. Is the paper by Ashwin and others from Exeter. It's a research group from Exeter, which I like a lot. And they provided somehow this extended the classical idea of bifurcation, which depend on changing a parameter, to explicitly treating the case of the rate of change of the parameter, as well as the finite size of noise leading to a tipping. So this is something that has been in my mind. And in the case of climate, because this is, if we go to the topic of the, let's say, physical area we want to focus, I think what has been very stimulating for me is that climate nicely has all the phenomenology of response to perturbations we have been mentioning. So there is smooth response, there are resonant behaviors, and there are obviously critical transitions that we call tipping point. So this is, and of course studying this is associated to some of the key problems in science. On one side, anthropogenic climate change, on the other side, evolution of life in our planet, and habitability in general, exoplanets. These are sort of almost metaphysical questions nowadays. And as I said, let's do I try myself some classification. So when we talk about smooth response, this is the range, this is the sort of piece in the world of theories, a meta theory where you can apply response theory to predict how a system responds to perturbation. So, and the information contained in the unperturbed system allows you to do this prediction. A fluctuation dissipation theorem is a special, very special case of this. And you are able also to predict time-dependent changes. So you are able to practically construct the so-called pullback attractor within approximation. So it's a recipe to construct these objects. Then you get close to the bifurcations, and this is signaled by the fact that nearby there are Polycott resonances, and here the system starts to behave strangely. So it stands as an example. This explains why you get a so-called slowing down near critical tipping points, near critical transitions. And finally, you go into the regime of critical transitions, and somehow the two pieces of the theory you need is, from the stochastic point of view, the Friedel-Wenzel theory and extensions, and from the deterministic point of view, the ideas, the very, very, amazing ideas of Grebogiot and York that Tamas described. So this, by the way, nicely fit with what's happening in the way people talk about climate change. So for a long time, climate change was associated to some sort of smooth response of a system to perturbations. So, and this has somehow, I think, led to the idea that it's easy to control it, maybe. Now people are focusing on using a different language, and I think an amazing, I mean, it was very interesting that The Guardian wrote a piece explaining why they're not going to talk about climate change anymore, which gives this impression of only smooth response, and they quote about climate crisis. Then each of us can think about whether this makes sense. I think there are a lot of elements in this, but the idea that the crisis also etymologically means something fundamentally different, okay? And so there is this nicely correspond to what I'm talking about. If we talk about the rigor of all of this, things becomes difficult in the sense that in most cases you would need very strong hypotheses, mathematical hypothesis to make statements. So you need to make working hypotheses. Just to be clear, if you didn't make something like an ergodic hypothesis, you wouldn't be able to treat almost any statistical mechanical system. If you didn't assume some robustness in the system, even writing a code for a numerical model, it's pointless. So you would be, you know, sort of rigid, unable to do any scientific step. So you have to make some working hypothesis. And when we talk about non-equilibrium, the working hypothesis we need is the chaotic hypothesis, at least for deterministic system. If we have noise, what we need is something like hypolecticity of the diffusion process, meaning noise enters and goes to all degrees of freedom. And I will mention this later. So a brief recap. In an early paper 2 years ago with Francesco Ragone and Frank Lucarini, we showed that indeed in a regime of smooth response, statistical mechanics allows you to do prediction of climate change. Then we tried to push things a bit harder, and this is some result with Andrei Gritzo, next speaker. We show that in some cases you find resonant behavior in the response. And this resonant behavior explains why the use of the fluctuation dissipation theorem is very dangerous and can be very misleading in climate. And I'll not elaborate on this because this is not the topic today. But basically you see features of the fact that the system is out of equilibrium. And this is work mostly due to Alexis Tanté, who is now a researcher in Paris. We saw that if you get close to the critical transition, which will be what I'm going to talk about, indeed, response theory flags the fact that you're near the cliff. Okay? So there is a continuity in these topics. They should not be looked separately. Now, let's look at just a cartoon to understand what is a critical transition. So somehow you see something like this. So you have some forcing with some protocol, and in some cases this leads to some sort of a smooth response. In some cases you jump to another state, and in some cases you have a sort of an intermediate behavior, and this is associated, somehow qualitatively to the idea that you have irreversibility in your behavior. Irreversibility, at least on a time scale long compared to the typical time scales of the system. I mean, I'm not talking about necessarily infinite time. Okay? So once we lose the Amazon forest, it's lost for a very, very long time. And once you are outside the European Union, it takes a long time, if ever, to go back. Okay? And this is fun. Now, next week there will be there will be a project meeting actually in this room, in this building, the project Types, which is a Horizon 2020 project that deals with the study of tipping points. So if anyone is interested, please let me know. We will have a lot of work in this research area. So now, going back to how you study transitions in multistable, let's say when you study transitions in multistable system, and specifically with reference to climate. So this is sort of the qualitative, what I would say, metaphorical way that is used, I think, in 99% of the publications in this. So the idea is that you observe a bistable, a two-peaks distribution. You associate to this two-peak distribution an effective potential and construct a Langevin equation that gives you this PDF. And then you change a parameter, and then you observe that you can go from one regime, from having a bistability to monostability, and you call this a tipping point. Okay? So in going back to the language before, so one stable state is Brexit, the other non-stable stable state is no Brexit. In between there are the bifurcations. So the thing that actually this movie, Melancholia, induced me to do is, instead of focusing on Brexit and no Brexit, is to focus on the negotiation. So focus on the saddle that Tamás so well described before me. So what is there that gives us the opportunity to understand the properties of the system? And what specifically in the case of the snowball snow-free transition? So this was something, of course, it's, I would say, one of the classic problem of paleoclimatology. And I tried to attack it in the 2010-9 using basically tools of non-equilibrium thermodynamics. And you learn things. If you introduce a concept of efficiency, you start to see the very different properties of these two states. But what are these two states? I mean, these states are very real. Indeed, our plan, now we are in the so-called warm state. But we have been, and we could be now, if we were a bit less lucky, in a state where the planet is covered by ice and with a temperature, typical temperature about 220 Kelvin, so practically devoid of life. And indeed, in the Precambrian, we did switch between these states a few times. And after the last switch, which left us where we are now, more or less, that's when multicellular life started to evolve. Okay, so you can think that each time you switch, you destroy life. And you know, this has interesting implications if you think about the search for exoplanets. There could be exoplanets in the habitable zone that could allow water, that have everything right. But too bad, they are in the snowball state, so no life, no party. Okay, that's and this is very real, of course. Okay, and now historically, for once, the theoreticians did predict something. So, in the sense that it was understood using the simple models Tamás mentioned, and that Michael indeed extended with adding more detail on the latitudinal structure. It was understood that such bistability exists in the equations. And of course, people said, oh, this is just mathematics, just equations. It cannot be true. It's very counterintuitive. It doesn't make physical sense. You know, this is a class. Remember, each time people say, doesn't make physical sense, means I have no idea why I'm saying this. That's mine after many years now in research. Oh, it doesn't make physical sense. I said, okay, whatever. A lot of things don't make physical sense, but happen indeed. And in later, evidence for this emerged. So there was, this phenomenon is very real. And I'm able now to skim through this and focus, because it was not mentioned before, what are the two main feedbacks that make this possible? If we have an instability, we need the positive feedback, which is not this. So we have first a negative feedback that stabilizes the system, provides a global stability, and this is given by the radiative feedback. Warmer objects emit more radiation and cool down. That's actually a very fundamental law of thermodynamics. And then we have something that is less fundamental, but it's very real. That is the positive feedback given by the so-called ice-albedo feedback. If I have if I have a cold anomaly, it's more likely. Remember, this is that snow will accumulate for longer periods or larger swaths of land, and this will lead to reflecting more radiation, and this will lead to cooler conditions. Okay, so that's the there are a lot of hypotheses here. There must be water. There must be a place where this water precipitates. There is a lot of ifs, but in our cases, and in many rocky planets, this could be true if there is sufficient water. So this is a positive feedback, and this feedback is responsible for the existence of three states So we have, as I mentioned before, we have two stable states, warm and snowball, and the unstable state, the saddle, which is the object of the interest today. If you see it on a classical representation of this, we have a classically bistability diagram, which is of course ubiquitous in many, many problems. And so in a range of parameters which are controlled basically the solar irradiance, how strong is the star, we have two coexisting states, warm and snowball, and the tipping point takes place when one of the stable state shakes hand with the unstable state, and they both disappear in a burst of light. Okay, and okay, so this is how our system looks like, and let me add that this is confirmed from the very simple model to the state-of-the-art IPCC class model. You get exactly this. Okay, and in not an IPCC class, but this was a PhD thesis of Robert Boschi in Hamburg, and we found this bistability for the model plasm that was described yesterday. I will not, so it's a simple climate model with still a lot of features. You get multistability, and you see in this graph where there is on the z-axis the globally average surface temperature, how naturally the three regimes of response exist in our climate in just one graph. So this is why I like this graph. Okay, now we want to discover this intermediate state that I will call Melancholia State for these sentimental reasons. And now let me give a slightly different, but similar in fact, description of what Tamás mentioned earlier. So we assume we have a dissipative autonomous system. The phase space contracts. We have two competing basins, two competing attractors, omega 1 and omega 2, two basins of attraction, and then you have a basin boundary. I mean, you can probably you can define this mathematically. So the basin basin of attraction is an open set. You take the two open sets, you take the complement of the two open sets, you take the intersection, and this is the basin boundary. So if you start from the basin boundary, you don't go to either attractor, you must go somewhere else because the phase space contracts basically. And this something else will be is the edge state mentioned before, and we call it Melancholia State because if we are talking about chaotic saddles. Okay. Now this is adding colors. This is going from sort of mathematical to air science description. Now warm is red, cold is blue, and the green is in between because why not? Okay. And so this is basically how the problem looks like in qualitative terms. And again, we want to study this M state in between. So this was the first major endeavor that of my collaboration with Tamás, ending up in this paper on nonlinearity, which was surprisingly, what people tend to like. Received the interest, including the presentation at Barbican. And what we did was constructing a slightly simplified version of plasm, still having the coupling between a slow component, diffusive ocean with ice-albedo feedback, and a fully dynamical atmosphere. So this is a system still with about 10 to the 4, 10 to the 5 degrees of freedom. With a lot, which is in the sort of usual state, is very, very turbulent. It has cyclones, it has whatever you want. And so, as they said, the atmosphere is described by primitive equations. So it's like a dynamical core. That's PUMA as open source model coupled to a diffusive ocean. So, and now you run this model, and miraculously, you end up with these two states again. So this feature is very robust. But we are interested in what lies between competing attractors. So now that's when we discovered, we got in touch indeed with Bruno Eckhardt. We paid a visit, Tamás, I, and Frank Lunkheit, in a cold winter day. We went to Marburg, and we presented our work on snowball state, and then we were said, look, we have been doing recently this work where we studied coexisting states in turbulent flows, in classically turbulent flows. You have coexistence of laminar state and long-lived turbulence. So it's different because the attractor is technically only one. Instead, in our case, our problem is cleaner because we have two competing attractors. So we are lucky, actually. So the idea is, how do I find what is in between the two attractors? And this was what we needed to learn. So what we learned about was the so-called edge tracking algorithm, which works like this. So actually, the idea is pretty simple, and now we are assuming we have two attractors and only one edge state. So all the points on the basin boundary are attracted to a set, which we call the edge state. So we take two initial conditions belonging to either basin of attraction, and by bisection, we found two initial conditions as close as we want on either side of the basin boundary, on the two sides of the basin boundary, that end up in the attractors. And now we send these orbits forward in time, and with the precisions that we can easily, more or less easily control, each n time step, we repeat the bisection method, and technically, in so doing, you are able to shadow a trajectory on the basin boundary. So you are killing the instability across the basin boundary. And then you wait, and I remember this was a surprising thing that the first time almost we tried, it worked. It's a very stable algorithm, and you end up in the edge state. So we presented these results. Actually, we were very excited, and I received a terrible reception to the work because someone told me, how do you assume, and this was Arkady Pikoski, he said, how can you assume that the basin boundary is a manifold? And the argument is, come on, I use the physical argument, right? Oh, it's 10 to the 4, 10 to the 5 degrees of freedom. Physical argument, whatever. Suggest me what else should it be if not a manifold? And he said, look, it can be a strange set, and it can have codimension smaller than 1. He said, come on, how can you see this in high dimension? My physical intuition tells me it's impossible. In fact, we were wrong, and he was right. So then we tested, and we found that you take 2 points on either side of the basin boundary, and then we took 1,000 points in between. These are initial conditions which are really barely distinguishable from each other. So the difference in the global average surface temperature is 10 to the 4 degrees, okay? And we found that along this line, we could find, with one, we gave, it was the trajectories going to the warm state, 0, the trajectory goes to the cold state, and we find some sort of very complex structure. That's what Tamash has been describing. So this was a huge surprise, and a huge surprise indeed to Ott, York, and Grebogi too, that, okay, you found this rough boundary in 10 to the 4, 10 to the 5 degrees of freedom. Nobody honestly thought that this was such easy thing to find. So this is a very robust feature. Message is, in many cases, the basin boundary is a gray zone where if you are there, you have no idea where you're going to end up. So this is a sort of a new concept about the basin boundary of coexisting attractors. It can be a place where, using the language of Lorentz, you have no predictability or very little predictability of the second kind, and this actually links with what Freddy was mentioning yesterday, okay? And this is a deterministic thing without noise. This is very real. And finite precisions, you don't have predictability of the second kind. Now, the source of this, and here where indeed the physical intuition became important and gave more meaning to the result, is that the condition leading to this bistability is the fact that the instability on the edge state is faster than the instability taking you outside the basin boundary. And in this case, the instability on the edge state is weather, and the instability taking you away is the ice-albedo feedback, which is on climatic time scale. So this is, luckily, the physical problem we attacked was perfectly suited to find the right, clear sign of the mathematical peculiarity here. So this was luck, I would say. Anyway, at the end of the story, indeed, one can find by stability, the edge, you find the warm state, you find the cold state, you find what we call at this stage, this melancholia state, which are chaotic. I will show you a movie, some of you have seen it, but it's quite impressive. You see weather in this edge state. And then there is a landscape, you know, then when you start to look into these objects, you discover a lot. Suddenly, you see a bifurcation in this chaotic edge state. All the system is zonally symmetric in the boundary condition, and at a certain value of mu is the relative solar constant, so mu is the current today's solar irradiance. You get a symmetry break, and this edge state breaks into a region that looks very warm and a region that looks very cold. It reminded us of a chimera state that has been very much studied in statistical physics. So you have a co-presence of, in a geographically nearby regions where let's say the atmospheric processes are very, very different. And there is a boundary, a sharp boundary between the two. We have not yet understood this at all. And this is the miraculous thing, in a range of mu, we get 3 climates. So we discovered the 3rd climate state. So it's not only 2 climates, it's 3. Now you dig in the literature and similar results have been found, but you know you need to add an ocean and a lot of processes. People have found a 3rd climate state, the slush bowl Earth, or there was another term by Pierre Ambert, I don't remember now. So states which are somehow intermediate between warm and snowball. And recently I had the chance to read a paper by the author, the first author is in the room, Maura Brunetti, and they discovered in a natural climate model 5 or 6 competing attractors. So I think the amazing story we are learning, and this is, I think, a potentially huge scope for research, is that the climate in a global sense is much more fun, much less trivial than we thought. There is not such a thing as climate state. There is a multiplicity of coexisting climates. And one might think of interpreting the ultra long climate variability, or the variability of planets we see, as the fact that we are sampling, and through noise we jump across this gigantic or not so gigantic basin of attraction. So I think this is very exciting. Now, briefly, we go to I want to show you, if I manage. Yeah, okay. Oh, it's I'm extremely clumsy in general, and now okay. So this is just to give a sense. This is the edge state, and you see that there are cyclones happening there. So the edge state is chaotic. It has definitely a positive first Lyapunov exponent, which was the easiest identification of chaos. Here you have a deterministic, you have a finite horizon of deterministic predictability. Now let's go back to the original, to the problem of noise-induced transitions. So somehow, is it possible to go back to this cartoon, but with this complex model and in a much more general setting? So what we did is adding noise in the intensity of the incoming solar radiation. So the star fluctuates. This leads us to multiplicative noise. So we put ourselves in a really bad corner here, but we try to keep something more realistic. So this is a more recent paper, also with Tamash, where we studied these transitions, and there is a longer preprint which is going through a long review. So now Tamash has already introduced everything. So I just want to emphasize that a fundamental, apparently, even if the literature is not entirely clear here, is that if you start with the stochastic differential equations, where the deterministic part, so where you look at the drift, is multistable, and you add the noise, and if you have a noise which defines a apoelliptic diffusion process, so the noise propagates from maybe few degrees of freedom to everywhere, thanks to the nonlinearity. Well, you are able to construct an invariant measure that looks like this, and phi is the pseudo-potential that can be constructed. There are few ways to construct it. Solves the Hamilton-Jacobi equation, as some one can say that in some cases it's not twice differentiable. It has some potential pathologies. I don't want to do into this. Nice thing here again is, I don't know if you can read it, because but in our case, since we are adding forcing noise to the sun, well, it's a good physical intuition tells us that this will propagate to all degrees of freedom, because the sun that sets the whole climate system into motion. So probably it's a good, we have been lucky here. So now again, I really don't need to add anything here. We study the rates, the transition rates, and we try to find evidence of that the inverse, in this case of the average transition rate, is controlled by the pseudo-potential and by the noise in this, through this law. So we studied 3 cases near the tipping point for mu equal 1 and for larger values of mu. And indeed, in the simple case, here I'm showing result for mu 0.98, we showed, we are plotting inverse of the noise versus permanence time, or inverse of the transition rates from one attractor to the other, and we find in logarithmic scale a nice fit, and it tells you indeed in this very complex system you can find the depth of the pseudo-potential well by studying transition rates. So this thing stands. And you also, we have been able to construct by averaging the instantons taking trajectories out of this attractor through the edge state to out. Yes, thank you, Michael. So it's somehow the nice thing is that you take a very complex system, you add a non-trivial noise, which is multiplicative, and without honestly putting, you know, this, we didn't do anything too sophisticated in terms of integrations and so on. We used the simple tools, no high-performance computing, and this thing works. So now we take a more interesting case, mu equal 1, so you have a substantial bistability, warm attractor, cold attractor, edge state. Things work as you expect. So the probability distributions peak over the deterministic attractor. If you go along the instantons, there is a minimum in the PDF exactly at the edge state, so it's a saddle, so things work surprisingly well. Now I go to the last part, very last part, and I talk about the impact of changing. Here, this is for a fixed value of noise, okay? If I change the noise, as implied from my earlier slide, if I increase the intensity of the noise, transitions become more likely, of course. Okay, so I go from a state of where I have very episodic transition to when they become more frequent. Of course, they are always more or less Poisson distributed, the jumps, but it just becomes more likely, exponentially more likely. And I will, now if I change, let's go back to the formula I showed before. So the invariant measure is written as a pre-exponential factor that is not interesting for us, times, and so we are all here talking in terms of large deviation approximation, the exponential of -2.5 is the pseudo-potential over sigma squared. So if you give me a sigma, let's say this is the invariant measure. Now I change sigma, so I reduce sigma. What happens is that, of course, the distributions will become more peaked. So this is one result, but there is another result, is that one of the two minima of the pseudo-potential corresponding to one of the two attractors, unless they have the same value, will become exponentially dominant over the other. So by switching off the noise, all the measure collapses, goes into one of the two attractors, and the other one is left empty. So if I take the zero noise limit, I don't get two measures, I don't get two ergodic components, I get only one ergodic component, the one corresponding to the lower value of the pseudo-potential. Is this surprising? No, because this is not an SRB measure. So the limit of the zero noise limit of the measure is not the deterministic measure. So this is the clear manifestation of this. So, of course, we could the individual trajectory could persist in the metastable state for a long time, but that's another story, different class of problem. So now, let's go back to our bifurcation diagram, mu, temperature. So this is a warm state, cold state, so, and melancholia state. This is the deterministic picture. I am doing a Linnaean classification of the phase space. Now I add noise, and things happen. So now this is the color tells you the density of states for each value of mu. So we see here that unsurprisingly, but this is again not in principle obvious, for low value of mu in the region of bistability, most of the time the system is in the cold state. And for large value of mu, most of the time the system is in the warm state. Now I reduce the intensity of the noise, and this picture becomes sharper. So this is more peaked, this becomes more peaked. Now I reduce more the noise, and I get this. So clearly there is a region in between where there is a transition. What is this transition? Well, now I'm plotting the population, so the fraction of the population of in the cold state and in the warm state as a function of mu for different values of noise, and look at the continuous line, which is the lowest value of the noise, and we clearly see that there is a transition which corresponds to a first order phase transition in my model. So there is technically a first order phase transition like liquid to gaseous. So for mu smaller, say, than 1, if I send the noise to 0, all the states will condensate to the cold. If mu is larger of 1.01, everything will condense to the warm state, and then of course we don't have a very good definition, and we're not even interested in finding the exact value of mu. Who cares? This is not we're not making prediction on this for the real world, but this first order phase transition does exist and is controlled by the difference between the value of the pseudopotential in the warm and snowball state. Final thing is that if you change the noise, the noise law, you change the instanton, but you keep the start point and the end point of the instanton the same, that is attractor and edge state. So at least in a projected space, if you plot, you don't assume you don't know where the edge state is, and you construct the instanton with the, say, 3 different noise laws, and you look at where these instantons in the phase space intersect, you can discover the edge state. So the edge state can be found also without the edge tracking algorithm, at least in a projected space. So this is something I would like to understand better, but I like it because we extract signal from noise in some sense. Okay, and we are trying to do this now in more complex models, but this is still ongoing. So concluding, I think the messages, 2 main messages of this are: first, we can and should have a thorough look at response of a non-equilibrium size system to perturbations in all regimes, from smooth transition to not so smooth to critical transitions. There is a way to look at this and have a comprehensive view. And in the case of climate, this becomes extremely relevant also for what are becoming the priorities of climate research. And the nice thing is we have been able to look at the classic problem of paleoclimate using somehow, without giving in too much, without renouncing too much to mathematical precision, trying to do as much as we could, and one can find nice evidence that the theory is robust enough that even if you cannot prove that any of the condition applies, it still works. And this is encouraging because it tells that this problem is workable. Okay? Thank you very much.
Okay, we are 5 minutes into the coffee break, but such a fantastic talk deserves questions.
So,
Well, I can pass it.
Thank you, Valerio, for this very nice talk. So, as you know, we are studying these kinds of problems since we are thinking of several applications. So the one about the bifurcation for the overturning circulation of the ocean, which is related to what's happening inside the glacial period. Or we are also looking at the superrotation state. So then a question I have is how can we really do physics with this, in the sense, so we have this very simple low-dimensional picture, so we know that it should apply to complex model, as you explained very well today. So, but the problem is that everything depends on the noise, everything depends on the quality of the model, and so for which phenomena can we say something which is actually meaningful, which is robust at the physical level?
Everything, thanks.
So, for instance, here in your case, a simple question would be, is the noise amplitude you use realistic?
Oh, yes.
So these kinds of questions. So how can we begin to address real physical question with this?
I mean, this is, I think, okay, first, the idea is we attack this problem, and not all problems are like this, because it's, there was a lot of robustness in the problem of snowball snowflake. So you expect that at least you find something that's meaningful, and it's not so model. So this is a case where it's not so model dependent. Other cases, of course, I mean, something in types we will be doing is also looking as an example at exactly thermal and circulation on this. And I expect that it also will find something that's similarly robust. We have not yet started, but we have some ideas also in Reading and so on. The intensity of the noise is key. I think the practice is you start with strong noise, and you start to see if you see any transition. This is not easy a priori to see any transition. So that's what I do. And then you can decide whether the intensity of the noise is unreasonable, but still the problem is worth looking at, and I will tell you in a second why, or if the noise itself makes the problem relevant. I think that also when the amount of noise you need to do see transition on reasonable time scale is much stronger than you will ever observe, still it's worth doing this, because studying these edge states and all the geometry is relevant also for a different class of problem, that is for basically impulsive forces. So let's make a specific example. Now, there was a recent article appeared, I think, not in the strict literature, but about the famous asteroid hitting the dinosaurs. Let's put it this way. So the asteroid that hit the dinosaur, of course, created a gigantic nuclear winter, monstrous. So the temperature, I think, dipped by 10-15 degrees. Okay, and almost, I mean, it killed a lot of the biosphere. Not all, but a lot. Now, the problem is maybe this asteroid was strong enough to kill the dinosaurs, but just not strong enough to let us jump into the snowball state, which could have happened. So in this case, I think, as an example, you see that the noise intensity to study this transition through sun, it would require a much stronger variability of the solar of the solar irradiance than what we really have in our star. But still we learn something relevant about the global stability of the system. That's my answer.
Well, let me maybe also comment that there are things that are just incredibly robust. The difference between the Boudico and the Sellers formulation of EBMs is fantastic, and the fact that the diagram in Barry Saltzman's book, has a lot of common properties with the one that I analyzed, is so again, the thing about snowball Earth having happened after all, is not surprising because it's fundamental, and again, it shows that instead of narrowing the gap between people who believe only in very detailed models and the ones who, think that there's some understanding in the simple ones, has grown rather than narrowed. Because in 1975, Suki Manabe wrote a paper with Weatherhold in which the then biggest GCM, which you can now run on your laptop, you know, showed the same kind of behavior. And so Suki clearly says that in the conclusions. You know, the fact that those people forgot to deal with the winds is not as important as the fact that we have the same behavior. You know, basically parabolic, you know, saddle node bifurcations and so on. And I also wanted to comment on the multiplicity of, you know, that you mentioned. Again, people don't read all the papers. There was a paper by Griffel and Drazen, I think roughly 77 or something like that, where they removed the symmetry about the equator that was kept by all the other people, including myself. And so, like in the thermohaline circulation, which I think Paola Cesi will be talking about, you have, you know, antisymmetric states. So the things with the sharp gradients and so that you see now in Plassim were also in, you know, in the 70s already. Ah,
okay. So as an effect of the, yes, in that case of the mismatch of the sun.
Yeah, removing the symmetry constraint.
Ah, okay, okay.
Okay, but I think that now we're not going to have coffee if we keep talking here, so let's thank again.
Thank you.